a couple more trips to Montreal within the next 1 month or so. So I might be coming together.
Okay, shall we get started? All right, so let's get restarted with the other types of geodetic measurements of fault deformation. I just thought that it is fun to look at how, besides GPS and INSAR, we can get down to really like a sub-millimeter scale of fault deformation with creepmeters. So creepmeters, as the name it means, they're measuring fault creep exactly on the fault. And the idea is that, so this is schematic. The top one is a schematic plot showing that the fault is this yellow band here. And the railway really doesn't serve any purpose other than just saying that it's trying to mimic this example in the real world where this railroad cut by the fault right over there. But the idea is that you put some kind of like iron rod across the fault. For example, here you can dig a ditch at some degree of angle from the fault, and then bury this iron rod at about 1.5 meters in the ditch. And then one side of the rod will be fixed and the other side will be left open. Now, if you have any kind of deformation on the fault, like this example here, this is a right lateral, very small creeping, like this is nothing to do with earthquakes, just a small creeping. But this right lateral small creeping is going to make this left side of the rod have some kind of displacement from its original position. And this position can be recorded at every minute or whatever time interval you would prefer. And that would create a continuous time series after some reconfiguration based on the geometry of the rod with respect to the fault. You can get what exactly, how much of displacement has occurred right on the fault at the surface. And this gives a very precise measurement down to 0.01 millimeter. So that's much better than what we get with GPS. Of course, there's a downside is that there is a certain amount of limit to it, right? It only measures small displacement. If you have an earthquake that's, say, 5 meter displacement, it will be completely off and it wouldn't work. So creepmeters measure slow, small, but accurate displacement at the surface of the fault. And turns out to be really useful in the study that actually we did for California is we look at a bunch of creepmeter stations. By the way, all the data is publicly available from USGS. So if you have a fault that you're interested in California, and then you can go to look at whether a creepmeter has been installed on it. Here we only plotted those ones that we looked at, but they're much more than this. This is probably a better view of creepmeter distribution in Southern California. But then you can go to look at USGS webpage and then get all this continuous time series for your purpose. So based on the ones that we have looked at, it seems that the creeping behavior can be categorized into two types. The first type is what we call this steady creep, like the blue lines is showing here. Okay, so I'm going to overlap with a different color. But steady creep is basically saying that there's not much of changing, except that there might be some fluctuations because of hydrogeological factors. So there's nothing like earthquake type or fault slip type of sudden movement. On the other, so this bottom here, this is also a continuous creeping record that you cannot associate any of the fluctuations to earthquake slip or aseismic fault slip. And the second type of slip is what we call the creeping events, where the amount of slip is still very tiny, because all from creepmeters, but you're starting to see the little steps in those. I'm not making it very accurate, but they're very incremental. And in terms of that, displacement is localized in time compared to the continuous creep. And the same thing here for this bottom plot here, which shows displacement after earthquake. But this is all post-seismic displacement. And we're seeing this, again, very stepwise of displacement on the surface. So again, I'm not showing the rest of the paper, but the idea is that the creepmeters can get you to very precise information on the surface. And then after that, you can try to distinguish how much of that displacement is because of, for example, temperature variation, because of precipitation variation, and the other types of hydrological factors versus tectonic factors that have contributed them. So that's one type of near fault surface displacement measurement. The other type of measurement that I thought is very interesting to introduce is to estimate earthquake slip, mostly earthquakes in the past, based on the coral records. So this works well for the marine environment, where especially we're looking at mech thrust earthquakes. We look at a large scale of uplift or subsidence because of the co-seismic slip and a post-seismic relaxation. So that kind of uplift or subsidence is very hard to record with GPS or INSAR because most of them take place within the ocean. So right now, some of the subduction zones have seafloor geology or seafloor GPS stations try to capture that, but not all of them. Certainly very expensive to instrument the seafloor. But if we're looking backward in time, there's this corals actually provides a very nice way to tell us how much of vertical displacement have occurred because of the sudden events and very rapid events, mostly earthquakes. So I took this example from Sumatra, where we had this 2004 magnitude 9.2 earthquake. That's this rupture area entirely here. As you can see, that's mostly entirely offshore. And then further to the south, we have 2005 Aeneas earthquake, much smaller. And then we have a sequence of earthquake toward the south. But again, as you can see that all the rupture are offshore, meaning that it's very hard to capture them if we can have far field GPS, but the near field displacement is very difficult to decipher. So this technique basically relies on the factor that this type of corals, the pyrites, they can grow radially upward and outward if it's entirely submerged in the seawater. But as soon as it's exposed to the atmosphere, the growth of the pyrite corals will stop or they become dead. So there will be a very clear mark between the live and dead corals. And if we're able to record how much of the uplift or subsidence has caused these orals to expose to the surface or re-submerge to the marine environment. And if we're able to also date those abrupt changes in life and death, then we'll be able to have very nice records of at what time in the history, how much of vertical displacement this particular spot has experienced. So that's the basic idea behind using the corals as an indicator for vertical displacement, especially for the near trench locations. So so for example, if I just look at maybe one of these corals here, that's the panel B. Now what this shows is, or let's just look at this part here. So this line is where the coral, or this would be the HLS, means the highest low tide, which is basically like the limit where the coral can be alive. So this will be the limit before that 2004 Sumatra earthquake, magnitude 9.2 earthquake, where on top of that, the corals have been dead, and then beneath that, they're submerged in the marine environment. And because of that 2004 Sumatra earthquake, this coral got uplifted by this amount. And then that's why we have the second line here. We call it pre-2005 event. So this is basically this amount of deformation is primarily due to the 2004 earthquake. And then this coral stays at this level for about, 3 months before it got uplifted again. Now, I don't have a scale here, but this coral has completely been uplifted, meaning that even this root is not above sea level. I think in the paper, they said that this total uplift is 65 centimeters. So this is an 18 centimeter scale. So this one is probably like a 15 centimeters of uplift from the Sumatra, the magnitude 9.2, and then another 65 centimeters from the magnitude 8.7, I don't remember exactly. Now this is interesting, right? This is telling us something about, even though that 2004 earthquake was larger, but the uplift was actually smaller for this particular coral because it was sitting much closer to that 2005 source area. So that's the basic idea of using the corals as indicator, a paleo indicator for the seafloor uplifting or subsidence. Now, what this Natawi Jaja paper showed is they basically went out to all those islands, hopped from one island to one to the other island, and those are the points that they have sampled for this entire along strike area. And then they would put together this record of corals and convert them into a relative sea level change as a function of time, mostly for the 20th century. So they can have a very nice time series of how much the seafloor has been fluctuating for hundreds of years. And that's very neat time record, not only for earthquake studies, but also for like climate type of studies.
Yajing.
Now with that, yeah.
What was the method used to date the coral growth?
I'm not sure. I'm not sure exactly what kind of dating method they used. I assume carbon-14, but I need to go back to read the paper of the dating. Yeah. So with that kind of deformation curve, like we see here, they can approximate with a constant rate with a black line, even though there are smaller fluctuations in the decadal scale. They can try to estimate what would be the kind of distribution of which part of the near trench area is experiencing subsidence and which part is experiencing uplift for the second half of 21st century. And if we go back to our original model of the co-seismic versus interseismic deformation pattern, is often that this change in sign in terms of the change from uplift to subsidence is telling us a lot about the lock-in depth of the McGill thrust fault. So this is how it can be useful in terms of McGill thrust earthquake hazard estimate. And you can go back in time as well for this particular plot. I don't even remember which one, this one, like where this came from, like the location. But for this record, they were able to infer that there was a McGill thrust event in 1797 that has caused the subsidence of this coral. And then, yeah, and then in the end, they construct paleo earthquake record for this entire Sumatra Trench, where we have this, this is modern record of the 2004 earthquake. And then they can go in to add more information about what they think that how much of the formation or how much of, so on the y-axis is seismic moment, is a representation of how much energy has been released. And this is as a function of latitude along the trench. So we're going from the north to the south. And this record really gives us a very, I wouldn't say very clear, but at least a rough idea of where, how much of energy has been released in the past. And more importantly, where we're still seeing this gap in terms of seismic energy release. And if it's completely locked, then this amount of energy has to be released in the future earthquake. Or if this part of the fault is creeping, then we can probably say that not much of strain energy would be contributing into a future earthquake. So yeah, so be able to estimate the displacement field associated with McThrust fault or any type of major plate boundary fault that has had earthquakes in the past is extremely important information for earthquake studies. Right, the last bit of it is, so we've looked at earthquakes, we have looked at post-seismic afterslip, we're also looking at interseismic loading. The only thing that we haven't looked at is something that we call it slow SSE, slow slip events. This is really relatively new observations in the past 10 or 15 years. Like really have changed our view of the earthquake cycle deformation pattern. And the discovery was made actually closer to home from the Northern Cascadia subduction zone. So this is a paper again from the Pacific Geoscience Center group, Herb Drager, Kelly Wang, James, I can't remember his first name. All right. Anyway, so right, so what do we have here? Those are the permanent GPS stations sitting on the Northern Cascadia subduction zone at the time of their publication. So what they have done is to look at, first of all, because of the subduction of the Wanda Fuga plate, so you would expect them to be moving toward the North American plate as this, the trend, right? That's the expected trend. And this is GPS time series at a station in Victoria as a time, so time is on the x-axis. So this would be what you expect. This trend is your expected interseismic locking rate or interseismic slip rate. But what happens in the summer of 1999 was that for about 1 month of time, those stations decided to move backward toward the ocean. So that's this red arrows, okay? And you can see they're in the opposite sense of motion from what's expected from interseismic loading. And they're even propagating along the strike direction. So this is distance along the strike going from south to north. And for this is about, let's say, a month of time. Very interesting behavior. And if you look at, come back to look at GPS time record, we can see that obviously there's not a very uniform displacement moving all the way toward the North American plate, right? So every once in a while, there is this seaward motion or opposite motion compared to what's expected. And if you just look at in a much smaller scale in time, and that's again the GPS record from I think stations near Victoria. So this is exactly what we're talking about, the reversed motion and then going backward to what's being pushed by the Wanda Fuga plate. And this amount of slip, if we add them all together, just use what we have done for earthquakes, do a GPS inversion, we can estimate where the energy comes from. That's roughly 30 to 50 kilometers. So beneath what we expect of the lock-in depth. And the moment magnitude, it's not an earthquake because it's very, very slow deformation, but the equivalent amount of energy released is about the same as a magnitude 6 or 6.5 earthquake. So imagine that a magnitude 6.5 earthquake has all its energy released within 2 weeks of time instead of 10 seconds. So that's why it's called slow slip events. And again, so people have done a lot of work to try to image where the energy comes from. So for example, this is one results from University of Washington group where they have looked at the maximum slip of around 3 centimeters coming from the depth. So this is about 40 to 50 kilometers in this case. Coastline is here. And then our estimated lock-in depth is roughly around the coastline. Again, there is debate about where the exact lock-in depth is, but at least we can safely say that this slow slip area is not directly at the lock-in depth. There seems to be a distance between the lock-in depth and where the slow slip is taking place. And on this right side, we're showing the schematic diagram where, again, we have lock-in depths and then slow slip going on there, possibly related to fluid being released from the dehydration reactions as the subducting slab goes down through those metamorphic phase transitions. Again, so the idea of high fluid pressure is something we inferred from seismological observations, where we can look at the ratio between P and S wave. So VPVS is a good indicator of how much of Poisson's ratio we might be expecting. And the higher it gets closer to 0.5, which is the ideal case for fluids, then we can probably say there is large amount of fluids within the source area. But again, I mean, what I try to emphasize here, those are indirect evidence of high fluid pressure from seismology, and then seems to be consistent with the metamorphic phase transitions.
Yajing.
Interesting.
Yajing.
Yeah.
A quick question on those slow slip events. Are these now becoming more and more recognized in most subduction systems, or are some systems do not have these slow slip events? And those that do have these SSEs, are they inhibiting major earthquake nucleation, or can they actually, increase the risk for megathrust activity?
Yeah, I think some of your questions can be answered by this slide here. Can you see yeah, so this is a summary from a review paper from Barroza and Satoshi Ide. So what they put together is the global distribution of where this kind of source events have been found around, well, they're all around subduction zones. And so, for example, Cascade is one of them, Alaska, mostly the southern and central Alaska, Nankai, southwestern Japan, New Zealand, mostly around North Island, and Mexico, Costa Rica. So they have been found in more than just one or two subduction zones, but certainly not in every subduction zone. For example, like people have been looking very hard in northeastern Japan, but they haven't been able to find those deep source events. There are a couple papers coming out talking about shallow source events, like slow earthquakes as they extend toward the trench. And those were based on the seafloor pressure gauge data. So there's a lot of debate of how reliable those pressure gauge data are, because you can imagine there are a lot of fluctuations going to the seafloor pressure. So it's not a, I guess my personal opinion, it's not a well-accepted discovery yet about those shallow source events in northeastern Japan. But it certainly seems to be widespread behavior for a lot of subduction zones. And there seems to be kind of, for example, if you look at Alaska, which is here, the slow slip are this green area, and the purple line is roughly the rupture area of 1964 magnitude 9. So there seems to be that source events are directly down dip of the rupture area. And that seemed to be, again, the same case for Japan, where those source events are directly down dip from the 1944, 1946 McThrust events. But if you look at Mexico, which is here, that those source events is certainly overlapping with the thrust faulting events. Some of them are not as like megathrust events, they're magnitude 7s. So, but there is certainly this degree of overlapping here. And especially in Costa Rica, that they seem to be totally overlapping in space. So Costa Rica is here. And this is why it's very important for Cascadia, because we don't really have a modern record of Cascadia McThrust earthquake yet. So right now we have lock-in depths that's again being debated by several groups, especially for those offshore of Oregon. But yeah, so if you just look at this kind of distribution of lock-in depths versus SOSIP, it's not very conclusive to me that the SOSIP events are definitely triggering McThrust events or prohibiting McThrust events. And then if we go back to the idea of Coulomb, right? So if you have a certain amount of slip on the fault, now that source area of the fault itself will get a stress release, while the area surrounding it will have a stress increase. So I think that spatial overlapping or the relative distribution in space of the source events and your future McThrust zone is very important in terms of whether those kind of magnitude 6 source events are going to accumulate in stress more and more in the seismogenic zone, or is it actually helping to release part of the stress, make it less likely to release it all in the magnitude 9. I guess I'm not sure if that answered your question, but I'm trying to probably say a bit of what I think of that problem. Okay, so I'm gonna move on to have the source scaling relations between those source events and how they compare to earthquakes. And this is interesting because we have lots of earthquakes every day on the Earth. So how we actually go around trying to recognize if this earthquake is different from the other one, or how this earthquake is different from a slow earthquake. So there is one thing called the moment duration relationship. So what we do, seismologists done, is on the x-axis, we plot the seismic moment, the representation of how much energy has been released. And on the y-axis, we plot the duration, so how long that rupture has lasted. And for earthquakes, typical earthquakes, that relation is roughly to the cube. So moment scales with duration to the cube. And this comes from our assumption that, I don't know if you guys remember that the for a wide range of earthquakes from like really small magnitude 1 to magnitude 9, the stress drop value seems to be quite constant across this range. So we can work out this relation between moment and duration using a constant stress drop. And those relationships between moment is the product of shear modulus times average slip times total area. So that's what's expected for regular earthquakes. But what has been seen from those small or slow events is a very different scaling, where the moment scales with duration directly. I mean, this is, again, a very rough simplification of that scaling relation. But what this is telling us is that if I'm going to release this amount of energy for a magnitude 6 earthquake, it will take me about, let's say, 5 to 10 seconds for regular earthquake, but it will take me, say here, several weeks to a month for our slow SIP events. And this is what like really defines slow SIP events. And then the question is why they are slow. So what is prohibiting the rupture to accelerate into the actual seismic SIP rate? Okay, that's just like putting actual data on the scaling relations to show that, look, there is really this distinction between regular earthquakes on this lower side and then slow earthquakes on the upper side. So there are a lot of mechanisms have been like introduced here to talk about the rupture speed being slow for those slow SIP phenomena, and then fluids seem to be one of the leading mechanisms. For example, people talking about dilation effects is that if you have like highly packed fault gouge material, and when you try to accelerate, increase SIP rate, transiently you're going to have increase in the void space or in the porosity of this gouge material, and that will make the pore pressure to drop temporarily. And then eventually that effective normal stress, which is the difference between your normal stress and pore pressure, will become higher because of that drop in pore pressure. So this is called a dilation effect. And then there have been quite a bit of work on this dilation effect, how this might actually slow down what could have been accelerated into seismic SIP. Right, I guess this is what, oh yeah, so this is a slide I want to conclude with is in terms of seismicity and fault zone, I guess there is really a lot of complexity in terms of the fault zone structure that we're looking at. For example, there is a long strike variation. First of all, is some part of the, so again, I'm taking McThrust fault as an example. There, some part of the McThrust fault is not as well locked as other parts. So this whole idea of asperity is that the asperities are representing areas has a higher degree of locking or more strain energy is being accumulating compared to other parts of the fault. And asperities could be of different sizes, even though they are all sitting within this broad range of seismogenic zone. Okay. And the second degree of complexity comes as we move further down dip from the seismogenic zone to this, we call it a transition zone. So transition is really an ambiguous word because it could be transition in a lot of ways. But in this sense, we're really talking about transition in terms of the stability, like whether it's able to accumulate energy toward the earthquake or not. So within this transition zone, you could still have little asperities that not as strong as those ones that in this locked zone, seismogenic zone, but occasionally some of them will be able to merge into a slow SIP events, or the smaller ones will express their energy in low frequency earthquakes, or so this VRF means very low frequency earthquakes, and seismologists are just not very creative in terms of naming their events. So they have go to low frequency earthquakes, very low frequency earthquakes, and there's a new name called URF, ultra low frequency earthquakes. It's just very confusing terminology in a sense here. But the very idea here is try to present this picture as a summary of what we have been talking through here. It's like this broad spectrum of fault deformation behavior that we are able to see partly from surface deformation could be coming from this very heterogeneous distribution of strength on the fault. So I think that's the end of my slide. Now, Laurent, I don't think we'll have enough time to cover the friction part for this fault, but again, I'm happy to let you distribute those slides to students. And then if they have any questions, they can send me an email to, and I'm happy to answer that as well. Do you think that is that a good way to, because in 15 minutes, I probably would like go through the introduction and then won't be able to get to much of that. But the good thing is that, so Christy and I, we talked a bit last week. What she's going to do is she's going to talk about the fault zone architecture. So like going from the core of the fault to the damaged zones, and then kind of across the fault, how the architecture of the fault zone will look like. And then she also will come back to this picture we're seeing right now about those heterogeneities and various degrees of heterogeneities on the fault. And then my slides that you guys will have a copy of it talks about friction on the fault, because eventually what's governing the strength on the fault is the frictional strength. So how friction evolves with slip. And so my slide focuses on the friction evolution under slow velocity loading conditions, and of representing the plate tectonics loading rate and how that's leading toward earthquake. And I think Christy is going to come back to friction, but talk about how the friction on the fault when it's experiencing an earthquake, where slip rate is several meters per second, and how we can see this dynamic weakening effect where friction coefficient basically drops from 0.7 to 0.01 within seconds of time. So yeah, I think there will be a kind of a continuity here for students to guess who are interested in the frictional problems. Okay, that's all I have.
We have time for maybe some questions.
Right, yeah.
University of Toronto or Queen students. Okay, well, judging by the silence, I gather not. We will, I think it's reasonable, Yajing, to stop at this point here. The notes are available on OnQ on friction, and I know that Christy will come back to it, and mostly from a dynamic friction perspective. These slides that you've posted, I seem to understand they're more on the static friction aspects of it. And that's fair. The quiz for this module is now posted on OnQ. And as in previous quizzes, you have until Friday afternoon to complete that. 60 minutes to complete. There are 8 questions in total. Other than that, the lab assignment on the Coulomb is due February 27th, which is not next Tuesday, but the following one.
So, Laurent, Queen's is having the spring break next week. Means that we'll have no lectures, is that true?
That's correct. So next week, there are no lectures. University of Toronto and Queen's are on reading week. Simon Fraser was this week. The following week is McGill's turn, correct?
Right, yeah. So I just checked with our IT office here. They will still be around, so we'll still be able to come in, or Christy or me will be able to come in, set up the teleconference, even though maybe our students are not going to be around.
Yes, as long as we can continue using the Zoom facility and software and record the lecture in 2 weeks' time, it's right. Simon Fraser's Dan Gibson that will lecture anyways. But if we can record it so that the McGill students can see it.
Yeah, we'll do that.
Perfect.
Okay.
Okay, thank you very much,
Yajing.
Right.
Thank you.
Thank you. Thank you.
Thank you.